Okay, we're back with part 3 of Review for Exam 2. Okay, question 5. A spherical balloon is inflated with air at the rate of 10 cubic feet per minute. All right, so that tells us that the volume of the balloon is increasing at this rate. All right, so this 10 cubic feet per minute, that's dV dt, the rate at which the volume is increasing. So let's write that down. All right, so we have here for number 5, we have dV dt is 10. All right. How fast is the radius of the balloon increasing? So we want to find dr dt. So what is dr dt? Okay. When the radius is 5 feet. When r is equal to 5. All right. So now we need a formula that relates V and R. That is the volume of a sphere. That will be our formula. Here's the volume of a sphere. The volume of a sphere is equal to 4/3 pi r cubed. And now we're going to differentiate both sides, so we'll have an equation with dV dt in it and dr dt. All right, so let's start differentiating with respect to t, like we always do for related rate problems. We always differentiate with respect to time. That's the rate has to do with how things are changing with respect to time. Okay, these are just constants, 4/3 and pi. Now we're differentiating r cubed, so that would be 3r squared, and then we have dr dt. All right, so we're ready now to figure out what dr dt is when r is equal to 5. Well, dV dt is always 10. We have that. All right, and now substitute in. Actually, these 3's are going to cancel here. But let's substitute in r is equal to 5. And then we just solve for dr dt. Okay, so like we said, these 3's are going to cancel. All right, so here we have 10, here we have 4 pi 5 squared. All right, so that's 5 squared is 25 times 4 is 100, so we have 100 pi here. And we'll just divide by what's multiplying the dr dt. We're going to divide both sides by 100 pi. Alright, and that's dr dt, 10 over 100 pi, or 1 over 10 pi. Alright, and let's see what are our units. Let's go back. Okay, we have the problem up here. The units would be feet per minute. Feet per minute. Okay, let's look at number 5. Sorry, number 6. Okay. Okay, number 6, we have sand is falling off a conveyor belt onto a conical pile at the rate of 20 cubic feet per minute. So this cone is increasing, the volume of the cone is increasing at this rate. So that tells us about dV dt. All right, let's draw a picture of the cone. So we have basically this is a pile of sand. Just draw it like this. And that's the bottom, the cone at the bottom, the circle at the bottom. Okay. And we're told that the volume of this cone is increasing at the rate of 20 cubic feet per minute. So that's dV dt is equal to 20. The diameter of the base of the cone is approximately equal to the altitude. All right, let's draw that picture. So here we have, let's see, here's just the circle at the base of the cone. All right, so let's see, here's the, let me just get, all right, let me draw the center here. Here's the diameter. And this is the altitude, this is the height of the cone. Sometimes we call it the height, here they call it the altitude. Alright, so these two distances are the same, this one and this one. Okay, I'll call the altitude h for height, and here this is d, and d is equal to two radii. Here's a radius and here's a radius. So d is equal to h. Alright, so as the sand piles up in this cone, the diameter of the base is always equal to the height as the cone increases in size. Alright, and let's replace d with 2r. The diameter is equal to 2 radii. So 2r is equal to h. Okay, and then we're asked at what rate is the radius increasing when the pile is 10 feet high. Alright, so we want to find out what dr dt is. At what rate is the radius increasing? So we want to know what is dr dt when h is equal to 10 feet high. So let's write down our formula for the volume of a cone. Alright, so we have the volume of the cone is 1/3 pi r squared h. Alright, now we're going to differentiate both sides, but before we do that, we want to eliminate one of these variables. We have two variables on the right, r and h, so we want to eliminate one of them. Now, when we differentiate, we want to have dr dt on the right-hand side because that's what we're solving for. So let's eliminate h. We'll put h equal to 2r. Alright, so we'll do that here. Okay, so here we have our 2r. And we're going to put h equal to 2r. So the volume is equal to 1/3 pi r squared times 2r. And just rearrange that, and we have 2 pi over 3. That's our constant. R squared r, that's r cubed. Alright, so now let's take dv dt, okay, or differentiate both sides. So we have here dv dt is equal to, now I'm looking at this, I'm differentiating this right here. Okay, I'm differentiating this. Okay. Alright, so I have dv dt is equal to just the constant, just so this stays in front, 2 pi over 3, and then we have 3r squared dr dt. Alright, now dv dt is always equal to 20, that we have from the problem. You see right here, 20. So let's put that in. Substitute in the 20 there. and we want to figure out what dr dt is when h is equal to 10. So we want to use that information. Okay, we can't directly substitute in h equal 10 because we have an r on the right hand side and not h. So let's observe that since we have 2r is equal to h, okay, so then if h is equal to 10, when h equal 10, we have 2r is equal to 10 and r is equal to 5. Okay, so that's what we'll do here. We'll substitute in r is equal to 5. Right, because when r is equal to 5, that's when h is equal to 10. So we'll do that substitution right now. So we have 2 pi over 3, and then we have a 3 5 squared dr dt. All right, let's cancel out those 3's here and here. All right, and we have 20 is equal to 2 pi times 25, and then we have dr dt. Okay, 20 is equal to 50 pi dr dt. Divide both sides by 50 pi, and we get 2 over 5 pi is equal to dr dt. Okay, and the units would be feet per minute. So that's how quickly the radius is changing when h is equal to 10.